Okay, we should know, and we've seen, and it's in previous videos, if you add r percent of p to p, it's the same as multiplying p by 1 plus r divided by 100. Reason for that is pretty straightforward. If necessary, you can investigate that. In any case, if you do that, then p, after being increased by p r percent of itself, becomes 1 plus r over 100 times p. If this is increased by r percent of itself, we get what? Well, we multiply this by 1 plus r over 100. And if we increase this by r percent of itself, what do we get? We get 1 plus r over 100 multiplied by this, which is, of course, 1 plus r over 100 multiplied by 1 plus r over 100 times p. Now, iterate n times, what do we get? Well, our first iteration is this, our second iteration is this, our third iteration is this. Doesn't this equal 1 plus r over 100 squared times p? Properties of multiplication, associativity, commutativity. We don't really need commutativity, but associativity. We can regroup this so that we have this with this, and this times itself is its square. And similarly here, we can use the same rules. And we get 1 plus r over 100 cubed times p. So, now we're not going to do an inductive proof. I'd kind of hope to get to that, but too many distractions and so forth. If we iterate this n times, it's fairly obvious what we're going to get. Every time we iterate it, we add another power. If this is what we get when we iterate it 3 times, then if we iterate it n times, we get 1 plus r over 100 to the n times p. Okay? Now, that's the bottom line. That's what happens. In introducing the problem, I used a little bit of notation for this quantity. Okay? I called this quantity, well, first of all, I called this quantity f of p. So we could write, now that we know about function notation, we could write f of p equals 1 plus r over 100 times p. Okay. What have we done here? We've increased f of p by r percent of itself. Okay. Now we could call that then 1 plus r over 100 times f of p. So this is 1 plus r over 100 times f of p. Of course, that's 1 plus r over 100 times 1 plus r over 100 times p, since this is what f of p is. Okay, then, at this stage, we could say, okay, well, this is 1 plus r over 100 times what we had here. Well, I didn't have a good name for what we have here, so I just used, without any need for anybody to understand function notation, I called this f with a 2 here of p. And I did mention that that's a little bit ambiguous notation-wise, because that could stand for the second derivative with respect to some understood quantity. But that's in a much different context than this. So, so I called this f2 of p, so I could call this 1 plus r over 100 times this. So we could say that this is f2 of p. And of course then this would be f3 of p. Now down here, there's no reason I can't call this f n of p, and that would be equal to 1 plus r over 100 times whatever we had before. What would we've had before? It would have been f n minus 1 of p. There's nothing mysterious in this notation, since I'm explaining and have explained what it means. It's not mysterious, it's just a little unfamiliar. I'm just using this notation to name what I have at each step, so I can talk at the next step about multiplying that thing by 1 plus r over 100. They might think that's unnecessary, because you might think, well, I've got this, once I have this formula, that's all I need. Well, for many applications it is, but in other discussions, you need a name for a simple name for the amount you get at each step. And that's going to be f of p, f2 of p, f3 of p, fn of p.